which is at 1 atmospheric pressure and 25 degrees centigrade. Normally it is defined. This is a standard state. So if I put that as G1 as G0, so G final, or let's say Gi is G0 plus RT ln P2 by 1. So this is becomes P2, or Gi is G0, 0 is now written top, RT ln P. So just rewrite that equation. This is the most useful equation. So Gi is Z0 plus RT ln P. This is one of the important concepts, right? Please understand, this is the pressure of Pi, of the gas. Okay, Gi is G0 plus RT ln P. We will make use of these equations to establish equilibriums, right? Now let's say we move on to an equation. Okay, now we say one mole of A, right, plus 1 mole of B gives rise to 2 mole of C. All in gaseous state, right? All in gaseous state. This is, so in a reaction chamber there is 1 mole of A gas, there is 1 mole of B gas, which gives rise to 2 mole of C gas. So let's say it's a spontaneous process. Let's say for it's a spontaneous process. So what is the free energy change? We want to estimate the free energy change for this process, right? Sorry. Yeah, we want to estimate what is the free energy change for this process. So how do we proceed? How do I proceed this? Let's say, so the final, free energy of the system is Gc. The free energy of the system is Ga. Let's say Ga. This is Gc, and this is Gb. Free energy of G. So the change is, there are 2 moles of C, so twice Gc minus Ga minus Gb. This is the free energy change, right? It's constant temperature. Temperature is constant. So delta G is 2Gc minus Ga minus Gb. So this is the free energy change for the system, right? Understood? So let's individually calculate Gc, Ga and Gb, right? Let's individually calculate this. How do I write Ga? Please note it, because I am erasing it. So pause the video if necessary, note it down. So Ga, what is Ga? So GA is basically G0 or right, let's put this here only. A is B. So GA is G0 as I have derived for any system. GA is G0 plus RT ln PA. Now what is PA? If there is a system like this, P is the partial pressure of gas A. P is the partial pressure of gas A. Similarly, GV is written as GA0 GB0 plus RT ln PB. Partial pressure of B is PB and GC is GC0 plus RT ln PC. So I will estimate the final free energies for A as this one, B as this one, and C as this one. Right? Once I have estimated the free energies, I will find out the change. So the change will be, please note it down, I am erasing it. So pause the video, note it down. Once you understand this, we will be solving a lot of problems that are normally asked. Reaction rate constant. We will talk about equilibrium constant or rate constant. Right? So delta G for 2C minus A minus B is 2GC minus GA minus GB, that is twice multiplied by Z0C RT ln PC minus GA0 RT ln PA minus, well, you can see it, GB0 RT ln PB. Right? If I do these calculations, so I will have in one hand 2GC minus GA minus GB, right? Right? So always also remember that we are calculating for this particular reaction, for evolution of 2 moles of GC, we are calculating the free energy change. Sometimes it is specifically mentioned that 1 moles of GC, what is the free energy change? I will talk about that. If 1 mole is given, you have to change this stoichiometric coefficients. I will talk about that. But the thing is that RT ln PC squared by PA into PB. This part is the most important part. Okay? So that is how we talk about this. And this is we call the standard free energy change. At a standard state, free energy change at a standard state. So from a standard state to any non-standard state, I can calculate the change in free energy with respect to the partial pressures of the gases existing in the system. right? Please note that there is a 2 RT ln, so 2 goes here. For logarithm it becomes the power, so PC square. There is no, the stoichiometric constants for A and B coefficients are 1, so this is 1 and 1. So if a reaction involves, like this, that the Na moles of A plus Nb moles of B to gives rise Nc moles of C, and you are asked to calculate the free energy change for Nc moles of C, so the generalized equation will look like change in free energy for C, for A plus B to C is standard free energy change for A plus B to C plus RT ln PC to the power NC divided by PA to the power NA into PB to the power NB. So the stoichiometric coefficients are raised to the powers of the partial pressure of the gases existing in the system. So normally this part, this PC NC by PA NA PV NB is written as Kp, the reaction rate constant, which is only a function of temperature. Please note it. The only variable, or when we'll do the VAC calculation, we will find it. It's only use of the reaction rate constant. Kp. So normally we write this equation, note it down, it's a very very important equation, this equation. So normally we write this as delta Gi is delta Z0 plus RT ln Kp. Ln Kp for partial pressure, if the concentration is kept constant, we write it in case. If it is expressed in terms of partial pressures, we normally write it P. If it is expressed in terms of concentrations, or activity, we term it as Kc. So del G is del Z0 plus RT ln Kp. So this is the equation. This is the equation we talk about. So from here we arrive at a very very important condition. Very important condition. What is the condition? It gives rise to a very important condition. Now, I always talk about equilibrium and delta G. This will be always, the talk of thermodynamics. This is always the importance of thermodynamics, to find out the equilibrium in terms of delta G. So whenever equilibrium and delta G is considered, always remember that the delta G, the free energy change, should be 0 if it is an equilibrium condition. That means Na moles of A and Nb moles of B is in equilibrium with Nc moles of C. So Na and Nb and Nc are all conserved. Nothing A and B is not converting into C. C is not converting into A and B. So this is the equilibrium. Right? The condition of equilibrium gives delta G to be 0. If I equate delta G equal to 0 for a particular temperature, to find out what is the partial pressures, if equilibrium is there, so it obviously will be delta G 0, and I also can find out what is the temperature at which the delta G will be 0. So from here I find out the delta Kp, the Kp value. so which is a T ln Kp is minus delta G 0. So Kp is exponential minus delta G0 by RT. So I can see the Kp is only a function of temperature because R and delta G0 are constant. This is a standard free energy change for a system. So R Kp is only a function of temperature. So at a particular temperature, the reaction rate is constant. So if you need to, if you need to play around the equilibrium constant, you have to change the partial pressures of the system. So you can find out that. So I will just write it again. That's a very, very important conditions and will solve a lot of problems as usual. So for this, Kp is given as exponential minus delta G0 by RT at equilibrium, which means delta Gi equal to 0, right? So delta Gi is delta G0 as RT ln Kp. Please note these equations. Spend some time with this equation. Just I will suggest you memorize this equation always. Because so many of the questions are asked from this one, these two concepts. I will discuss those problems which appeared in previous year's GATE's question paper for metallurgy. So the concept of reaction rate constant in terms of free energy change, that is standard free energy change, RT temperature, and reaction rate constant and delta G free energy change. Right? That is the concept. Okay, fine.